Okay, we'll start a new topic today, which will be perturbation theory. Okay, our first look at it will be the time-independent version. Okay. So what is perturbation theory? Okay, what is perturbation? Okay, perturbation is something which you have in a system which modifies the system just a little bit. Okay, you may have a small effect which makes a big change in the system. Okay, that's not considered as perturbation. Okay, a perturbation is something, it's a small effect and results in a small result, small consequence. So we have been solving equations which look like H, okay, some psi n equals En, okay, psi n, right? So this is some set of problems we have solved, but they are almost all of them are quite idealized. The particle in a box, okay, the harmonic oscillator, the spherical problems, the spherical box, the hydrogen atom without, okay, many other effects that we could have included. Okay, so we have something which looks like this. Now, this H is the idealized H is something that we can actually solve directly. So this is something we are going to call this as the zeroth order equation. And okay, we have the exact solutions. So this is our starting point. We have exact solutions for this. So anything that we did during the first semester, solving all those problems or hydrogen atom, etc., is the zeroth order approximation. And just to show that it's zeroth order, we just put, okay, so the notation is going to get a little messy for this discussion. We are going to put a superscript 0 to all of these things, which means this is the solution that we already have. Now, what happens when there is some additional interaction, okay, that is in the Hamiltonian? So I have now H0 plus some additional, okay, effect. Then I cannot solve the problem. If you can solve the problem, of course you can go ahead and solve it, then you can make that your H0, okay? But this is usually something that we cannot solve exactly. So we are going to do an approximation. So the result of this, okay, is that these H and the psi's and the energies are going to change. So there will be changes in those things, which in general will be, okay, proportional to H squared. Remember, this is an operator, so I'm just using these terms somewhat loosely. So there will be corrections to this psi and E proportional to H squared, proportional to H cubed, etc., okay, which we call higher order terms, higher order corrections. Now, to keep track of what is going on, we put here a coefficient, okay, we'll call it lambda, okay, and we'll at the end set lambda equal to 1. So this is just a device for us to keep track of powers of H, okay? So I said first power of H, second power of H, third power of H, which doesn't make sense for an operator because H can come in various ways. But this lambda will be just a variable so that we can describe everything in powers of lambda, and then at the end we can put lambda equal to 1, but it's just a device for keeping track of things. So when I take this H0 and turn it into something like this, then what happens is that this psi n0 now goes into psi n0 plus psi n1, okay, plus psi n2 dot dot dot, okay. Now, since I told you that we are going to arrange the orders of this approximation according to these powers of h, what we are going to do is we are going to, okay, say this is going to be proportional to 1 power of lambda. This is going to be proportional to lambda squared and so on. Okay, so eventually we are going to remove that lambda, but it's just going to help us do that. And similarly, this En0, energy of the end state, will similarly go to En0 plus lambda En1 plus lambda squared En2, etc. By the way, you can use this analysis, okay, for many problems. Whenever you can solve a problem exactly, if some piece is missing, some small piece is missing, and you want to include the effect of that missing piece, you can always do some analysis like this, okay? It doesn't have to be an even eigenvalue equation. This is a nice technique in order to just systematically expand the results of a small effect. Okay, so now what I have to do is I have to write my Schrödinger equation like this, and you see it's going to be a nice long equation, but I am not worried because you'll help me. Okay, so I'm going to have my Hamiltonian that's going to have just the 0th order and the 1st order term. Okay, and then that is going to operate on our psi, which is going to be psi n0 plus lambda psi n1 plus lambda squared psi n2 dot dot dot, okay, is equal to the energy, which is going to be En0 plus lambda En1 plus lambda squared En2 plus dot dot dot, and the wave function again. Psi n0 plus lambda psi n1, okay, plus dot dot dot. Okay, so now the idea is when you multiply this out, you take terms with equal powers of lambda and solve those equations. Okay, for example, the 0th order equation, okay, we have already there. Okay, so if you look at lambda to the 0 terms in this equation, you are going to get that, right? Lambda h0 psi n0 is equal to En0 psi n0. All other terms are going to have powers of lambda in them, okay? So the excitement starts with lambda equal to 1. So let's see what we are going to get now. Okay, so first order, which means I'm interested in lambda to the 1. Okay, so let's see. I have h0, so let me just write those things down. You see, I'm not even going to write the lambda. h0 psi n first order. Okay, so that's lambda to one term here. There's another one, plus h1 lambda h1 0. Okay, so you can see that when I add the orders, I get 1 in each of these terms. Okay, 1 plus 0, 0 plus 1 is equal to, okay, the right-hand side. Again, I have just two terms. This zero order term, first order term, first order term, zero order term. Okay, so I'm going to get En0 psi n1 plus En1 psi n0. All right, so this is our first order equation. So let me just play around with it. Let me take this, okay, this whole equation is equal to that, okay, and find the inner product of that with psi n0, okay? So what do I get? I'm going to get psi n0 h0 psi n1, okay, plus psi n0 h1 psi n0 plus En0 psi n0 psi n1 inner product, and plus En1 psi n0 psi n0. All right. Now, let's at this point open a parenthesis. I'm going to get terms here which look like psi n0, psi n1. Okay? Now, what do these things correspond to? Well, I have these psi n, okay, 1 for example. That's the first order correction to the wave function, right? So this is a function, and I should be able to expand it in terms of eigenstates of the Hamiltonian. So this function, I should be able to expand, okay, let's put in a k here, some ck times psi n0. How do I find these ck's? Well, very easy. So ck is going to be equal to psi n0 psi n1. Okay, so that's exactly that. Now, you see, I can find any one of these coefficients like that. So in some sense, I'm obtaining the coefficients from that equation. But we'll design our, okay, functions in a certain way. Yes?
Hocam, are we just summing over k's then, or n's?
This is for the certain n. Okay, so this is for a certain n. Okay, so the c obviously will depend on n. Okay, so there's a hidden index here if you like, but I'm just looking at the equation for a single n. Okay, so for particular n.
Yeah, I was wondering, can't we just take the psi n0 outside? Do we have it like that in that case?
Oh, okay, I see what you mean. Okay, thank you. That's important. This is k, obviously. Okay. Okay. So it's just an expansion in terms of these psi k's. But what we are going to do is we are going to say these psi n1 does not contain any term with the same n index, okay? So for example, if this is the ground state, if this is psi 0, there will be no ground state in this expansion. So all the ground state function that I need, I'll keep it in the original psi 0. Now you can say, how can I do that? Okay, how do I have the freedom to do that? I ordinarily would not have the freedom to do that, okay, if the wave function was normalized. If the wave function is normalized, the amount of psi 0 that I have inside the original wave function would be fixed. But I am going to now release the normalization. I'm going to say that the normalization is such that, okay, the normalization of the wave function is such that I have each one of these eigenstates, the psi 0 eigenstates, are all in the 0th order wave function. Okay, so the 0th order wave function contains all the psi 0s, for example, that are in also higher order expansions. Okay, so I have a psi 0, certain psi 0 here, which I am expanding like this, but these things that I have here, okay, so these objects that I have here do not contain any psi n zeros. Okay, so that's a requirement that I put in. Okay, so these things have no psi n zero contribution. Okay, so that will of course mean that although the original wave function may be normalized, my total wave function is not necessarily normal. In fact, it usually will not be normalized. Okay, so I'll have to normalize it later. But that will make my life a lot easier. Okay, so what that means is this.
Perturbation does not have extra degenerates, right?
Okay, no, perturbation. Okay, so the question is, what about degeneracies? At this point, we are assuming that the perturbation is so small that it's not making a major change in the problem. Okay, it's not lifting or introducing degeneracies. We'll look at the degenerate case separately. Okay, so what that means is that I am going to get, okay, this is also going to be k right over here. I am going to get 0 for psi n0, psi n1. Okay, so in fact, all, yes?
The psi 0 term will be k and psi 1 will be n in the CK definition.
Yes, yes. Okay, let's see. Psi n. Okay.
In the bottom one.
Let me see. This is k. CK. Let's see. Psi n1, psi.
Yeah, n will be k and.
Yeah, okay. What do I have here? Psi and k, right? Okay. So what I will be assuming is that there will be no contribution. Okay, so let me just perhaps write what the result is. The psi n0 contribution in any one of these psi n, okay, a number greater than 1, j, okay, is equal to 0 for j greater than 0. Okay, so for higher order terms, there's no contribution from the 0th order state, 0th order wave function. So that means I'm going to get a 0 here. Not only that, but this term also, okay, because H0 now operating towards the left, this term is just equal to En0, right? Because psi n0 is an eigenstate of H0. So it's going to be psi n0, psi n1. And we just say that this is also going to be 0. Okay? So what am I left with? I'm left with this term.
Equal sign in place of the...
Yeah, okay, I missed a... Okay, you'll get it right eventually, okay? So, and this term here is 1 because it's just psi and 0, psi and 0. Okay. Yes.
Did we say by saying the psi n0 and psi times psi nj equals 0, are those higher order states orthogonal to the zeroth order solution?
Well, yes, they will be orthogonal. But the reason they will be orthogonal is that because there will be no contribution in their expansion by construction, okay? By the way we are constructing it, there will be no psi n0 term in those things, okay? So these coefficients we are going to determine, and when we are determining them, we are going to make sure that this coefficient is always 0. Okay, so now let's look at what we have obtained once more. So the only non-zero terms are, let me write the term on the right first. En1 is equal to psi n0 h0 psi n0. Okay, so this says first order change in the energy. So this is an important quantity now. First order change in the energy is equal to the expectation value of, oops, this should be 1, right? Otherwise, okay. Expectation value of the perturbation, okay, with respect to the state that I am analyzing. So this says solve your equation, obtain psi n zeros. Okay, so we have the exact solutions. Now that we have found these eigenstates, find the expectation value of the perturbing Hamiltonian there. Okay, that is going to give you the first order change in the energy. Okay, so that sort of makes sense, right? If you, for example, if I am interested in finding, okay, so suppose I have some electron wave function. I have some electron wave function which goes like that, and another electron wave function which goes like that, assuming that there is no electron-electron interaction. But now, suppose I want to find the effect of the electron-electron interaction to first order. What does that say? Well, that says, okay, take one wave function, okay, and psi 0, put in the electron-electron wave function, that's going to be something R1 minus R2, whatever, and multiply it by psi 0 again. So find the expectation value of this Hamiltonian, okay, this perturbing Hamiltonian, okay, with respect to the original wave functions. Obviously, these wave functions are going to change also, but that will be a higher order change, okay, because here we are looking at the first order change, so there should be only one first order object in these results. So you see you get 0, 1, 0, okay, and 1 here. So everything here is from the original solution except H1, okay, and that gives you a change in the energy, right? Yes.
Over there, next to the how can the first order Hamiltonian can act on psi n1, which has no psi n0, and how can we get E n0?
No, okay, it's just this equation. Okay, so if you just look at this equation, it is H, okay, which is in this form, and this is psi. So this whole thing is acting on the whole wave function is equal to this whole energy and that. Okay, so if I could obviously do this problem exactly and find out all the terms in the series, then I would get an exact wave function here, etc. Okay, but what we are doing now is we are just looking at this equation systematically, and we are saying, okay, I'll equate equal powers of lambda to one another. Okay, so on the left-hand side, I take terms which are first power in lambda, which are those, okay, equal to same terms on the right-hand side.
But in the first term, how can we handle like that 0 for the Hamiltonian act on an object which not
This one?
below that?
Okay,
Next to that.
yeah.
So the first term right to that one.
This one?
Yeah, that one.
Okay.
The zeroth order Hamiltonian is acting on a first order object which has no zeroth order.
Okay.
And we get the zeroth order energy.
Okay, but this psi n 0 is an eigenfunction of h, right? So, okay, so this, since it's a Hermitian operator, it will work towards the left. Okay, so it will just give the eigenvalue. Okay, other question? Yes.
We said that lambda is equal to 1, but what exactly is lambda? Is it the...
It's just, lambda is just a tool for us to keep orders together, okay? You see, I'm not even using lambda. Okay, so I could have said, okay, there's no lambda, okay? So another strategy for teaching this would be, okay, suppose there's no lambda, I don't put lambda anywhere, but I say that now let's group terms so that the orders add up to something, okay? So I could say, let's take all the terms which are 0 on both sides. Or I could say, let's take all terms in which the orders add up to 1. So I take 0 here, 1 there, and 0 there. Okay, so, but it's easier to just put in the lambda. It's the same thing. Okay, just a counting process. Okay, questions? All right, so while we are at it, let's also look at how the wave function is changing, and then we'll do some examples. You see, and this will be a pattern. We'll always be able to find the energy to any order using wave functions from a lesser order. Why? Because if I want the energy to some kth order, okay, I'll have h1 here. So everything else must be less than k in order. Okay, so that the order is always the kth order. So the wave functions that I am going to use to obtain some order of correction is going to be the ones that I have from the previous order. So here I have wave functions from the 0th order, which I can use to determine the energy to first order. Okay, so let's go on. So I'll just take the same equation, okay, the first order equation. I already found an inner product of it with psi and 0. But now what I'm going to do is I'm going to take an inner product of that with a different object. Okay, so all of that started with psi and 0, okay, inner product with the first order equation. Now I'm going to take a different psi k 0, okay, with the, okay, first order equation. Okay, so we are just going to do the same thing, except that I'm just going to take the inner product with psi k 0. Okay, so let me try to do it step by step. So psi and k is not going to be equal to n. Okay, so now I'm looking at other terms. So what will that give me? That will give me psi k0, okay, h1, psi n1, okay, plus psi k0, h, I already started with a mistake, right? No, I'm okay. Psi, okay, h1, yeah, okay. This should be 0 and 1, okay. So it should all be first order again. It should add up to first order. So psi k0, h1, and psi n0 is equal to E n0 psi k0 psi n1 okay, plus E n1 psi k0 psi n0. Okay, so we have something which looks like that. All right, so let's look at these things. The easiest one is this one, psi k0 psi n0. What was that?
0.
That's 0, right? That's our discussion over here. Okay. So if I have these things different, then I have okay, no, these are the original wave functions, right? They are orthogonal anyway, so that's 0. This one, now that's, I have to be careful about, but let's look at this object here. This, you see, is 0, that is 0, those are the original functions. So this will operate towards the left and it will give me ek, okay, 0th order, psi k0 psi n1 plus, okay, I have an h1 here, so I don't have any eigenstates, so that's going to stay psi k0 h1 psi n0, okay, is equal to, okay, that's 0, so I have E n0 psi k0 psi n1. Okay, so I have, you see, psi k n1, psi k n1 on both sides. What's that? That's the expansion coefficient for the series. Okay, so let's find out what that is. So, okay, let me move this towards the left and then divide. So psi k0 psi n1 is equal to, okay, I'm going to introduce a new notation. If I have the original wave functions 0 and 0, okay, which are sandwiching any operator, I am going to call this thing H1, okay, the operator, and a matrix element Kn. Okay, so it's the Kn matrix element of H1 with respect to the original states. So this is going to be equal to H1 Kn divided by, I have to get the order right, En 0 minus Ek0. Okay, so this is how much the wave function, first order wave function, is changing. Okay, so psi n1 is going to be equal to a summation over k, but I have to skip n. That's what we discussed over there. I'm not going to get any contribution from n itself. Obviously, I'm going to get into trouble if n is equal to k. This is the expansion coefficient, H, first order matrix element Kn, divided by En0 minus Ek0. Okay, psi n0, k0, I'm sorry, psi k0. Okay, so this is the first order change in psi n. Okay, remember our expansion. This is the first order change in our psi n due to H. And I have this H, matrix element of H entering in, so it depends on how much H will connect K and N. Okay, so the explicit form is over here. So I have to take the expectation value, not the expectation value, but the matrix element of H1 between states K and N, the original states K and N. That gives me this matrix element. I divide that by this En minus Ek. So states which are closer to one another in energy are going to give larger contributions. Okay? And I just sum over all the contributions except I skip N. Okay? So there's not going to be any N0 contribution here, and therefore we'll have orthogonality and such things with that state, but no contribution from that, and that's what I have. Okay, so that's really the first order energy results. Okay, so this is one of them. The first order change in the energy is again given by just, well, let me write it in matrix form, H1 N. Okay, that's what I have over there. Okay, so the diagonal matrix element and matrix element is going to give me the change in the energy. All right, any questions? Yes.
How do we know the Hamiltonian of the first order perturbation in the first step?
Okay, someone has to give us something, right? We need a problem to solve.
But
If we don't even know the Hamiltonian, then we should. Okay, we have bigger problems.
But besides the problem, I mean, while we try to calculate these things in some research or so.
Okay, you usually start with the Hamiltonian, which usually is, if it's a nice realistic Hamiltonian, which usually is very complicated, which you cannot solve. So the first thing you do is try to see if it is, okay, if it resembles something that you know, okay, from undergraduate or graduate physics, okay, so you say, oh, okay, so this part of the Hamiltonian looks like what I have learned earlier in such and such a course, okay? And that's something I know, okay? And then you look at your Hamiltonian, now there's this extra term, then you can say, well, okay, let me start with what I know and see the effect of what is added to it. Okay? All right, so let's look at an example. Okay, as an example, the simplest thing that we can look at is particle in a box type of problem. Let's suppose we have our, H0, if v equal to infinity there, v equal to infinity there, minus a over 2 to a over 2. Okay, and we have something like this. So this is our v of x, and our h0 will be minus h bar squared over 2m d squared dx squared plus this v of x. And we know how to solve this. Okay, so this is our h0. This is unperturbed Hamiltonian, and we are going to get solutions to it. Okay, so we are going to get all these ENs, okay, which are going to be h bar squared over 2m pi over a squared n squared, right? Those are the energies, and we are also going to get the wave functions. So let's just write them as u n's are equal to some normalization, and either I have cosine n pi over a x or sine n pi over a x. This is for odd n, and this is for even n, right? So these are our un zeros, if you like. Okay, so these are the original states. Now, suppose what I do is I add an electric field to the problem. Okay, so suppose, I add an H1, which is going to be, some extra potential E times X, right? So that will give me, well, I also need something like E0. Okay, so the minus sign. So this corresponds to, so if this is my extra potential, this corresponds to an electric field in the X direction, right? So what does that potential look like? Well, that additional potential looks like something like this. So it makes the right-hand side of the box a little more advantageous for particle. Okay. So if I put something like this in, what is going to be the change? Okay, so these are zeroth order energies again. I am interested in what the zeroth order change in the energy is going to be. Well, very simple. It's going to be H1, n. So that's going to be equal to, I have these wave functions. Let me look at the ground state, 1, 0. So it's going to be a cosine function. So it's going to be cosine squared pi over a x, and the normalization is what, 2 over a or something, a over 2 over a, something like that times x times dx.
So isn't it En?
Hmm? Yes, I also need all that stuff, right? Minus ex e0. Hmm? Excuse me?
We have wrote En0 equals H1, but
En1, I'm sorry. So, okay, dx. All right, but now you see this is symmetric integral minus a over 2 to a over 2. This is even, and that's odd, so I end up with 0. Okay, so this is sort of typical of response of simple systems. We'll see that there are exceptions, but usually when you apply an electric field that polarizes the system, so you get a polarization. So the energy is going to be that polarization times the electric field. So it's going to be proportional to the square of the electric field. So to first order, you don't get any energy change, okay? But you will get a polarization, okay? So the wave function, which we don't have enough time to work around, but the wave function, which was initially something like this, okay? So this was our original wave function, u1, 0. If we calculate what u1 first order is, okay, it will be something which looks something like that, okay? Which means that the total wave function, when I add them up, is going to, okay, be something like that. So the particle will shift from the origin. So it means it's going to have some polarization, right? It's not going to be symmetric now. The average value of x is going to be positive. Okay, so particle will more likely be on the right-hand side. Now, if you look at the energy of this, remember that the energy due to a dipole, okay, a polarized material inside an electric field is electric field times the dipole. So we are going to get one electric field from the particle polarization, another electric field, okay, multiplying that. So the change in the energy, okay, so the change in the energy, En2, is not going to be 0, okay? So that's typical of the response to electrical perturbation. Okay, so this, for example, how we get a Hamiltonian. Okay, we have a problem which we know how to solve, and then even if you make a small change on it, something like adding an electric field, then we are going to get a reasonably complicated problem. Okay. All right. There are no questions. I'll let you go. Okay. Okay.